Get things that look about like this. Um, so for the tension, things are going to change at 0.25, zero point 0.5, and then uh, goes out to 1. So we started at positive 142.8. Then we drop way down to negative 69.28. So let's see. There, there, and then it stays here. For the shear force, um, it starts at negative 464.5. Then it drops down to negative 7535.5. And then it jumps up to positive 4,000. And the bending moment, I didn't calculate what these values are, but these are all linear functions. And um, it starts out with a small slope of negative 464.5. Then you get a bigger slope, and then you get that.
121 and negative 2,000 about
What?
negative 121 and about negative
Okay.
120-ish,
And then this one's what?
negative 2,000.
Okay. All right, so there are a couple things to notice here. The first is that at each um, at each one of these locations of a point force, you get jumps of the type that you have in your point load. And I mean, you actually could have point couples too, like a picture like a screwdriver being, twisting at a point. That's a point couple. Okay. I mean, these are just point forces. But what we had is we had a horizontal force at 0.25, right? And so we got a jump in the tension, the internal tension, and this magnitude is the magnitude of this jump is equal to the magnitude of that horizontal force. You know what I mean? That horizontal force was 7,071. The magnitude of this jump is 7071. Okay? Here at 0.25, we had a jump of 7071 because the magnitude of the vertical force at that point was 7071. And that's how I knew I didn't have to calculate what these, like I just took shortcuts in calculating this graph because I knew these would match up. I knew this region would end where this region started, and this region would end where this region started. And the reason I knew that is because there weren't any point couples. Okay? If there were point couples, you'd get jumps in the bending moment of a magnitude equal to the magnitude of the point couple. Okay? Um, so jumps in the tension, shear force, and bending moment correspond to the magnitude of the horizontal force, the vertical force, and the point couple, respectively. And both of these two things I'm telling you to notice, are really good ways to check your answers. They're not really useful in coming up with answers, but they're just things that you can use when you're done to say, like, yeah, everything looks like it makes sense. Um, actually, as sort of a corollary of this, how did I know that this was going to end at 0, that this bending moment diagram was going to end at 0? Because there's no point couple in this problem applied at the end. You know, there's no, the thing isn't fixed to a wall at the right side. Okay, so there's no couple there, and therefore you can't have anything but 0 at that point. Okay. The second thing I want you to notice is, I mean, we wouldn't want to say we've proved a theorem or something, but this does always turn out to be the case, and you can look back and see that it holds in this. The derivative of the bending moment is equal to the shear force. Okay, that's always going to hold. Okay, there's one more question I want to ask. Oh, this is sort of an intuitive question, philosophizing type question. How does it work that our last cut, so we did these diagrams based on these cuts, right? How does it work that we never did a cut that included that load at the right side? And yet, you know, like doesn't that load at the right side affect what these diagrams will look like? Like, how can that be? I mean, what if instead of a load of, where's the problem? Instead of this load of 8,000 newtons, if I applied a 15,000 Newton load, that would affect what's going on internally, right? I mean, it has to. So how does it come about that we never see those in the cuts?
When you do it at the very beginning.
Yeah,
All time.
that's exactly right. So if you applied a different external load at the right side, you'd get all different external loads when you isolated the whole thing as a, you know, the thing as a whole. And then those different external loads are what we use then when we make those cuts. Okay, so sort of it's the information about the right side sort of sneaks in the back door based on our first calculation. Okay, so I think that's another point that sometimes confuses people. Like, how does that work? It works because we do use that load in the first step. Any questions about this? So next time we'll go on to internal loads with distributed loads.